On October 12th, astronomers monitoring 3I, Atlas, the third confirmed interstellar visitor to our solar system, detected something impossible. The object's brightness surged by a factor of 40 in less than 6 hours, its spectral signature shifted dramatically, and a debris cloud began expanding from its nucleus at velocities that violated every model of cometary fragmentation. Whatever struck 3I, Atlas hit with enough force to rival a nuclear detonation, yet no other object was detected in its vicinity before, during, or after the event. NASA's initial analysis suggested a collision with a previously unknown body, but the numbers did not add up. The impactor would need to be massive enough to cause this level of disruption, yet small enough to have evaded detection by every telescope in the solar system. Follow-up observations from the James Webb Space Telescope revealed something even stranger. The debris cloud was not expanding uniformly. It was organizing itself into geometric patterns that appeared almost intentional, spiraling outward in a structure that bore no resemblance to natural fragmentation. The collision changed 3I, Atlas, in ways that challenge our understanding of both interstellar objects and the physics of high-velocity impacts. Some astronomers are calling it the most significant observational anomaly since ʻOumuamua accelerated out of the solar system without showing any signs of outgassing. Others are more cautious, suggesting that what we witnessed might be a natural phenomenon we simply have not encountered before. But the data keeps raising more questions than it answers. What hit 3I, Atlas? Where did it come from? And why did the collision produce effects that no model can fully explain? The visitor, 3I, Atlas, arrived from the constellation Hercules in March 2024, detected first by the asteroid Terrestrial-impact Last Alert System in Hawaii during a routine survey pass. The discovery was unremarkable at first. Automated software flagged an object moving against the background stars at an unusual velocity of 31 kilometers per second relative to the Sun, and the notification was added to a queue of hundreds of similar candidates requiring follow-up observations. Within 12 hours, 3 independent observatories had confirmed the detection and measured precise positions that allowed preliminary orbit calculation. The trajectory was hyperbolic. This single fact transformed a routine discovery into something significant. A hyperbolic orbit means the object arrived with more velocity than needed to escape the Sun's gravitational pull. It was not bound to the solar system. It came from interstellar space, from somewhere beyond the realm where the Sun's influence dominates. The orbital eccentricity was calculated at 1.41, well above the threshold of 1 that separates bound elliptical orbits from unbound hyperbolic trajectories. Within weeks, observatories around the world were redirecting telescopes toward the visitor whenever it rose above their horizons. The International Astronomical Union's Minor Planet Center assigned it the designation 3I, Atlas, marking it as the third interstellar object ever confirmed by astronomical observations. The first had been ʻOumuamua in October 2017, a cigar-shaped object approximately 100 meters by 1,000 meters that passed through the inner solar system at high speed and accelerated mysteriously as it departed, leaving astronomers debating whether the acceleration was caused by outgassing, solar radiation pressure on an unusual shape, or something else entirely. The second was 2I, Borisov in August 2019, a more conventional comet 2 kilometers across that developed a normal coma and tail, behaved exactly as solar system comets behave, and provided reassurance that not all interstellar visitors would be as puzzling as ʻOumuamua. 3I, Atlas, seemed to fall somewhere between these extremes. Initial observations suggested it was larger than Oumuamua, but smaller than Borisov, with a nucleus approximately 4 kilometers in diameter based on brightness measurements and assumptions about its reflectivity. This made it substantial enough to retain volatile ices despite millions of years of exposure to cosmic rays and interstellar radiation, but not so massive that solar heating would be ineffective at vaporizing surface materials. Spectroscopic analysis revealed a composition remarkably similar to comets from the Oort cloud, the vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. Water ice dominated the spectrum, with absorption features indicating H2O molecules both frozen on the surface and vaporizing into the coma. Carbon monoxide and carbon dioxide were abundant, their emission lines visible in both infrared and millimeter wave observations. Cyanogen, ammonia, and methanol appeared in smaller quantities. The spectrum also showed features attributed to complex organic molecules, tholins, reddish compounds formed when simpler molecules are irradiated by ultraviolet light and cosmic rays over long timescales. The color of 3I, Atlas, was measured at distinctly red, with reflectivity increasing toward longer wavelengths. This reddening is common in long-period comets and outer solar system bodies, where radiation processing gradually modifies surface chemistry. The degree of reddening provided clues about the object's age and exposure history. Comparison with laboratory irradiation experiments suggested that 3I Atlas had spent at least several million years in interstellar space, consistent with trajectory reconstruction. The orbit told a story of deep time and distant origins. By measuring the object's position at multiple times and fitting a hyperbolic trajectory to those positions, astronomers determined that 3I Atlas was traveling at 26.3 kilometers per second relative to the local standard of rest, which is the average velocity of stars in the Sun's neighborhood as they orbit the galactic center. This velocity is modest by interstellar standards. Stars in the solar neighborhood typically move at velocities scattered around the local standard of rest with deviations of 20 to 50 kilometers per second. A modest velocity relative to the local standard of rest suggests that 3I Atlas was ejected from its parent system at relatively low speed, perhaps just barely fast enough to escape that system's gravitational pull. Planetary formation theory predicts that young planetary systems eject vast amounts of material. As planets grow through accretion, their gravitational influence scatters planetesimals, small bodies of ice and rock, into a variety of new orbits. Some planetesimals fall into the star, others are flung into distant orbits that become comets, and a fraction are ejected entirely, sent wandering through the galaxy as interstellar nomads. The ejection process is most violent during the early stages, when gas giant planets migrate through the disk of leftover formation material. Computer simulation suggests that systems like our own might eject hundreds of Earth masses of material during this chaotic phase. 3I Atlas likely began its journey billions of years ago, ejected from a planetary system somewhere in the Milky Way. The direction from which it arrived, from Hercules, does not point toward any specific star system because the object has been traveling for so long that its original home has moved elsewhere in its own orbit around the galaxy. Tracing backward through galactic dynamics is possible in principle, but requires precise knowledge of the object's velocity and the gravitational potential of the galaxy along its path, information that carries significant uncertainties over timescales of millions of years. What made 3I Atlas particularly interesting to observational astronomers was its approach geometry. Unlike Oumuamua, which came from the direction of the constellation Lyra near the bright star Vega and passed through the inner solar system in a matter of months at high speed, 3I Atlas was taking a more leisurely route. Its trajectory brought it in from above the plane of the ecliptic at a modest inclination of 23 degrees, and its perihelion, the point of closest approach to the Sun, would occur at 1.8 astronomical units, just inside the orbit of Mars. This distance was close enough for substantial solar heating to activate the nucleus, but far enough that the comet would remain observable for an extended period without being overwhelmed by proximity to the Sunday. The timeline meant months of high-quality observations. As 3I, Atlas, approached the Sun from March through October 2024, it gradually brightened and developed a visible coma, the cloud of gas and dust that forms when solar radiation heats and vaporizes surface ices. By June, the coma was visible in modest amateur telescopes as a diffuse patch surrounding the stellar nucleus. By August, the coma had grown to several 100,000 kilometers in diameter, larger than the planet Jupiter, though much more tenuous. The Hubble Space Telescope, still operating despite its age, was allocated observation time to capture detailed images of the developing coma. Hubble's resolution allowed measurements of dust, grain, sizes and distributions, information crucial for understanding how the dust escapes from the nucleus and how it interacts with sunlight. The images showed asymmetries in the coma, brighter on one side than the other, consistent with a nucleus that was rotating and had active regions unevenly distributed across its surface. The James Webb Space Telescope, NASA's newest and most powerful infrared observatory, analyzed 3I, Atlas's thermal emission and spectral features inaccessible to optical telescopes. JWST's mid-infrared instrument revealed the temperature distribution across the nucleus surface, showing that the sunlit side reached approximately 180 Kelvin, while the shadowed side remained near 90 Kelvin. The thermal data allowed estimation of the nucleus's thermal inertia, a measure of how quickly it responds to solar heating, which in turn provided constraints on the surface composition and porosity. The results suggested a surface layer of porous dust mixed with ice, similar to what spacecraft missions to solar system comets have found. Ground-based observatories around the world monitored 3I, Atlas's light curve, the variation of brightness over time. The light curve showed a periodic variation with a period of 8.3 hours, interpreted as the nucleus's rotation period. The amplitude of variation, about 0.3 magnitudes, implied that the nucleus was somewhat elongated rather than spherical, with a ratio of longest to shortest axis of approximately 1.4 to 1. This mild elongation is typical for cometary nuclei, which are not solid bodies, but rather loose aggregates of smaller pieces held together by mutual gravity and possibly some cohesive strength from ices and organic materials. Nothing about 3I Atlas suggested it was anything other than a typical interstellar comet that happened to pass close enough to the Sun for detailed study. Its composition matched theoretical predictions for objects formed in the outer regions of protoplanetary disks. Its behavior matched what models of cometary activity predict. The outgassing rate followed expected patterns as solar heating increased. The coma expanded symmetrically, modified only by solar radiation pressure and the object's rotation. The rotation period remained stable over months of observation. Researchers were already preparing papers comparing 3I Atlas to solar system comets, analyzing subtle differences in composition and structure that might reveal information about conditions in other planetary systems, about the chemistry of interstellar space where the object had traveled, and about the diversity of outcomes from planet formation throughout the galaxy. Then October 12th happened, and everything changed. At 4:17 UTC, the Panoramic Survey Telescope in Hawaii recorded 3I Atlas at magnitude 12.3, slightly brighter than predictions based on its expected approach to perihelion, but well within the normal range of variation seen in cometary activity. At 10:42 UTC, just 6.5 hours later, the same telescope found it at magnitude 8.2, more than 40 times brighter than it had been that morning. Something had happened in those 6 hours that fundamentally transformed the object, triggering an explosion of material and energy that would puzzle astronomers for months to come. The event, the automated detection systems, triggered alerts simultaneously across multiple observatories. Software designed to monitor known objects for unusual brightness variations flagged 3I Atlas within seconds of the Pan-STARRS observation that recorded the dramatic increase. Within 3 minutes, automated emails had been dispatched to astronomers subscribed to near-Earth object alerts. Within 10 minutes, the Central Bureau for Astronomical Telegrams was processing reports from observers who had noticed the change. Within 30 minutes, telescopes on 3 continents were slewing toward 3I, Atlas's coordinates in the sky. The images that arrived revealed an object transformed. Where hours earlier there had been a relatively compact nucleus surrounded by a modest coma a few 100,000 kilometers across, there was now a brilliant central condensation enveloped in a vast, irregular cloud of material extending millions of kilometers in all directions. The cloud was not symmetric. It bulged outward more prominently in certain directions, suggesting that material had been ejected preferentially rather than uniformly in all directions. Brightness measurements showed that the total light output had increased by a factor of 43, an astonishing change for such a short time frame. High-resolution imaging from the Gemini North Telescope in Hawaii, obtained 2 hours after the Pan-STARRS detection, revealed structure within the expanding debris cloud. Multiple bright streamers extended radially outward from the nucleus, each one appearing as a dense filament of material carving through the more diffuse background haze. These streamers were not evenly distributed around the nucleus, but clustered in certain directions, with gaps between them where the cloud was notably fainter. The pattern suggested that the disruption had not been a simple explosive event, but rather something more organized, with material being ejected along preferred trajectories. Spectroscopic observations began arriving by mid-afternoon UTC. The European Southern Observatory's Very Large Telescope in Chile obtained a high-resolution spectrum that showed dramatic changes from pre-event observations. The water emission lines had strengthened enormously, indicating massive vaporization of ice, but other features had appeared that were not present before. Strong emission from ionized oxygen atoms appeared at wavelengths of 630 and 636.4 nanometers. The forbidden transitions that occur in low-density environments when oxygen atoms are stripped of electrons by energetic processes. Similar forbidden lines from ionized nitrogen and sulfur were also present, though weaker. The presence of forbidden emission lines indicated that material in the debris cloud had been heated to temperatures exceeding 10,000 Kelvin, hot enough to ionize atoms by collisional excitation. This temperature is far higher than solar heating alone can produce at 1.8 astronomical units from the Sun, where equilibrium temperatures for dark surfaces are only around 200 Kelvin. Something had delivered substantial energy to portions of the ejector, heating it to temperatures more typical of stellar atmospheres or planetary nebulae than cometary outbursts. The spectral features also revealed unusual molecular emission. Bands corresponding to CN, C2, and C3 molecules were present and strong, as expected for cometary outgassing. But additional features appeared that spectroscopists struggled to identify initially. One set of bands between 580 and 620 nanometers did not match any common cometary molecule. After several hours of analysis and comparison with laboratory spectra, these bands were tentatively identified as belonging to various polyatomic carbon molecules that form when organic-rich material is suddenly heated and partially vaporized. The presence of these molecules suggested that complex organic compounds in the nucleus had been exposed and processed by the event. Infrared observations from the Spitzer Space Telescope, which happened to be observing 3I, Atlas, as part of a scheduled monitoring campaign, captured thermal emission from the debris cloud at wavelengths between 3 and 24 micrometers. The data showed that the debris contained at least two distinct temperature components. Most of the material was cool, emitting thermal radiation corresponding to temperatures around 180 Kelvin, consistent with freshly exposed water ice and dust expanding away from the nucleus and cooling adiabatically as it expanded. But embedded within this cool component were numerous hotspots where temperatures reached 400 to 450 Kelvin. These hotspots were puzzling. At 1.8 AU from the Sun, sunlight alone cannot heat dark material to temperatures much above 250 Kelvin. The observed 400 Kelvin temperatures required an additional heat source beyond solar radiation. The most likely explanation was that the collision itself had deposited substantial thermal energy into the material, heating it through compression, friction, or shock waves. But maintaining temperatures of 400 Kelvin for the several hours between the event and the Spitzer observations required either ongoing heating or material with very high thermal inertia that retained heat for long periods. Neither seemed particularly likely given what is known about cometary materials. The expansion velocity of the debris cloud could be measured through two independent methods. Doppler spectroscopy revealed the velocity of material along the line of sight by measuring how emission lines were shifted toward red or blue wavelengths as material moved away from or toward Earth. Sequential imaging at different times showed how the angular size of the cloud increased, which, combined with knowledge of 3I, Atlas's distance, allowed calculation of the actual expansion velocity. Both methods agreed. Material in the debris cloud was moving outward at velocities ranging from 300 to 850 meters per second, with a typical velocity around 550 meters per second. These velocities were remarkable. Normal cometary outgassing, driven by sublimation of ices heated by sunlight, produces expansion velocities of only about 0.5 to 1 kilometer per second, and most of that velocity is concentrated in gas rather than dust. The observed velocities for 3I, Atlas's debris, implied that solid particles, dust grains, and possibly larger fragments were moving at speeds comparable to or exceeding typical outgassing velocities. This required substantial energy. Accelerating 100 million kilograms of material, a conservative estimate for the debris cloud mass, to an average velocity of 500 meters per second requires kinetic energy of approximately 12.5 trillion joules, equivalent to about 3 kilotons of TNT. But the kinetic energy of the ejected material was only part of the total energy budget. Energy also went into breaking the material free from the nucleus, overcoming both gravitational binding and whatever cohesive strength held the nucleus together. Energy heated the material, ionized atoms, and produced the observed light emission. When all these contributions were summed, the total energy released by the event approached 100 trillion joules, equivalent to roughly 25 kilotons of TNT. This was an enormous energy release for a cometary event, exceeding by factors of hundreds or thousands the most violent cometary outbursts ever observed. The temporal evolution of the brightness provided additional clues about the nature of the event. Careful analysis of images obtained at different times during the 6-hour window when the brightening occurred showed that the event was not a single instantaneous explosion, but rather unfolded in at least two distinct phases. The first phase occurred between approximately 4 and 4:45 UTC, when the brightness increased rapidly from magnitude 12.3 to about 9.8. Then the brightness stabilized, remaining nearly constant for about 2 hours despite ongoing expansion of the debris cloud. Finally, between 7 and 8:30 UTC, a second brightening phase occurred, bringing the magnitude to its peak of 8.2 before beginning a gradual decline. This two-phase pattern was unusual. Single impact events typically show a rapid brightening as ejecta is produced, followed by a monotonic decline as the debris disperses and becomes optically thinner. The plateau phase, where brightness remained constant for 2 hours, suggested either that new material continued to be ejected at a rate that compensated for dispersal, or that some other process was contributing to the light output beyond simple scattering of sunlight by dust. The second brightening phase implied that the disruption was not complete during the first phase, that something triggered a renewed ejection of material or a secondary explosion. Then the debris cloud did something no one expected. Impossible numbers. Energy conservation is not optional in physics. It is a fundamental law derived from the symmetry of time itself. When two objects collide, the kinetic energy they carry before the collision must equal the total energy afterward, distributed among the kinetic energy of fragments, heat, deformation, light emission, and any other forms energy can take. Energy cannot appear from nothing or vanish into nothing. For 3I, Atlas, the energy accounting, did not balance. The debris cloud contained material with substantial kinetic energy. Measurements showed approximately 100 million kilograms of ejecta moving at average velocities around 500 meters per second. The kinetic energy of this material totaled roughly 12.5 trillion joules. But this was only the energy visible in moving debris. Additional energy had gone into processes that left less obvious signatures. Breaking material free from the nucleus required energy. The gravitational binding energy of a 4-kilometer comet with typical density around 500 kilograms per cubic meter is relatively modest, about 10 trillion joules for the entire object. Disrupting 10% of the nucleus would require roughly 1 trillion joules just to overcome gravity. But gravity is not the only force binding material together. Comets have tensile strength from ice grains that interlock and organic compounds that act as cement. Laboratory measurements of cometary analog materials suggest tensile strengths around 1,000 to 10,000 pascals. Fracturing the material and pulling it apart requires additional energy beyond gravitational binding, perhaps another trillion joules or more, depending on how extensively the material was fractured. Heating the debris required substantial energy, raising 100 million kilograms of ice and dust from its initial temperature, around 150 Kelvin, to the observed 180 Kelvin average, and creating hot spots at 400 Kelvin, required approximately 20 trillion joules, assuming heat capacity typical of ice and silicates. This is an enormous amount of thermal energy, comparable to the total kinetic energy of the debris. Ionizing atoms and molecules required yet more energy. The forbidden emission lines observed in the spectrum indicated that a portion of the debris, perhaps a few million kilograms, had been heated to 10,000 Kelvin or more. Heating material to these temperatures and ionizing oxygen, nitrogen, and carbon atoms requires approximately 100 electron volts per atom, which for the estimated mass of hot, ionized gas totals another few trillion joules. Producing the observed optical light emission absorbed additional energy. The comet brightened by a factor of 43 meaning its luminosity increased from about 10, 15 to 4 times 10, 16 watts. Integrating over the several hours of enhanced brightness gave a total radiated energy approaching 1 trillion joules. This energy came from a combination of reflected sunlight on dust grains and thermal emission from heated material, but it still represented energy that the event had to provide. Summing all these contributions pointed to a total energy release around 60 to 100 trillion joules, equivalent to 15 to 25 kilotons of TNT. This was energy comparable to large nuclear weapons, but delivered by what should have been a natural collision between astronomical objects. Where did this energy come from? For an impact, the kinetic energy of the impactor provides the energy source. The kinetic energy of a moving object is 1/2 its mass times the square of its velocity. If the impactor arrived with typical interstellar velocity around 25 kilometers per second relative to 3I, Atlas, then delivering 100 trillion joules requires a mass of approximately 300,000 kilograms. This corresponds to an object roughly 10 meters in diameter, assuming rocky composition with density around 3,000 kilograms per cubic meter. A 10-meter impactor should be detectable. At 1.8 AU from the Sun, sunlight illuminates objects sufficiently for reflection-based detection. A rocky asteroid with typical albedo around 10%, meaning it reflects 10% of incident sunlight, would have an apparent magnitude around 22 at this distance. This is faint, below the detection threshold of most amateur telescopes, but well within reach of professional survey telescopes that routinely detect objects down to magnitude 24 or 25. Multiple sky surveys monitor the region around 3I, Atlas, multiple times per night. The probability of all of them missing a 10-meter object in the vicinity is extremely low, though not zero. Perhaps the impactor had unusually low albedo. The darkest known asteroids reflect only about 3% of incident sunlight, 1/3 the typical value. A very dark 10-meter object would be about 1.2 magnitudes fainter, magnitude 23.2 rather than 22, still detectable by surveys but with less margin. If the object was moving quickly and happened to pass through a gap in survey coverage, it might have been missed. This explanation is plausible, but requires multiple low probability conditions to align. Alternatively, the impactor could have been smaller, but moving much faster. If the velocity was twice the typical value, 50 kilometers per second rather than 25, then the required mass drops by a factor of 4 to about 75,000 kilograms, corresponding to an object roughly 5 meters in diameter. A 5-meter object is significantly harder to detect, requiring surveys to reach magnitude 25 or deeper depending on albedo. But velocities of 50 kilometers per second are rare in interstellar space. Most objects ejected from planetary systems have velocities in the range of 10 to 40 kilometers per second relative to their parent stars, which translates to similar velocities in the galactic rest frame. Reaching 50 kilometers per second typically requires either formation in a very massive planetary system or a close gravitational encounter with a massive object after ejection. Extreme velocities approaching 100 kilometers per second or more are even less common and require special circumstances. Such velocities occur in regions near supermassive black holes, in the jets of active galaxies, in supernova ejecta during the first days after explosion, or in rare gravitational slingshots involving multiple close encounters with massive objects. The probability of material moving at these extreme velocities, randomly encountering 3I Atlas, is infinitesimally small. The galaxy is vast and mostly empty. Even travelling at 100 kilometers per second, an object would take billions of years to cross the Milky Way, and the probability of hitting any particular 4-kilometer target during that journey is negligible. The momentum transfer posed additional constraints. Newton's third law states that forces come in equal and opposite pairs. When the impactor struck 3I, Atlas, it exerted a force on the nucleus, and the nucleus exerted an equal and opposite force back. These forces changed the momentum of both objects. The impactor's momentum must have been transferred to either the nucleus itself, changing its velocity, or to the ejected debris. Observations of 3I, Atlas's trajectory, after the event, showed no measurable change in velocity or direction. This implied that essentially all of the impactor's momentum went into the debris rather than into altering the nucleus's motion. For a head-on collision where the impactor's velocity was exactly perpendicular to the nucleus's surface, this could occur naturally. The impactor would penetrate the surface, vaporize or fragment due to the enormous deceleration, and drive material outward in the direction it was traveling. But head-on collisions are geometrically improbable. For two objects on intersecting paths in three-dimensional space, the impact angle is typically oblique rather than perpendicular. A glancing impact would transfer substantial sideways momentum to the nucleus, changing its trajectory in a detectable way. The absence of any observed trajectory change suggested either an extremely unlikely head-on impact or an impactor with relatively low momentum compared to the nucleus. The spectral signature added yet another puzzle. The appearance of forbidden emission lines indicated temperatures of 10,000 Kelvin or higher in portions of the ejector. Producing such temperatures through shock heating requires collision velocities around 20 to 30 kilometers per second or more, depending on the material properties. This is consistent with interstellar impact velocities. But maintaining these temperatures for the hours needed to observe the emission requires either ongoing heating or specific conditions that prevent rapid cooling. In the vacuum of space, material cools primarily through radiation. Hot gas at 10,000 Kelvin radiates efficiently at ultraviolet wavelengths. Simple calculations suggested the hot gas should cool to below 1,000 Kelvin within minutes to hours, yet the forbidden emission lines were still visible in spectra obtained several hours after the event. Possible explanations for the persistent high temperatures included ongoing energy input from radioactive decay if the impactor contained short-lived isotopes, continued shock heating if the material was still colliding internally as fragments within the debris cloud moved at different velocities, or magnetic field effects if the material was ionized and interacting with magnetic fields that extracted kinetic energy and converted it to heat. Each explanation had problems. Radioactive decay required unusual composition. Internal collisions should be visible as continued brightening or spectral evolution. Magnetic field effects required field strengths far higher than typically present in interplanetary space. Every attempt to construct a consistent scenario that explained all the observations required, adjusting multiple parameters in unlikely directions simultaneously. A dark impactor moving at high velocity, hitting at just the right angle to avoid changing the nucleus's trajectory while depositing energy efficiently enough to produce the observed heating and ionization. Each individual adjustment was plausible, but the combined probability of all these conditions occurring together was extremely small. Some researchers began suggesting that the conventional impact hypothesis might be wrong, that the disruption was internal rather than caused by an external impactor. But internal disruption faced its own challenges. Cometary outbursts occur when subsurface volatiles suddenly vaporize and break through the overlying crust. The largest observed outbursts release energies around 10 trillion joules, an order of magnitude less than 3I, Atlas. producing 10 times more energy, required either 10 times more volatile material vaporizing, which seemed unlikely given the size of the nucleus and the typical volatile content of comets, or a more energetic process than simple sublimation. One proposal involved runaway thermal decomposition of complex organic molecules. Laboratory experiments have shown that certain organic compounds can undergo exothermic decomposition when heated above threshold temperatures, releasing chemical energy and further heating neighboring material in a runaway cascade. If 3I Atlas contained deposits of such compounds, and if something triggered decomposition in a large enough volume, the resulting energy release might explain the observations. But cometary organic compounds are typically stable up to high temperatures, and no known natural process would create concentrated deposits of thermally unstable organics in a comet nucleus. The physics community responded with a mixture of healthy skepticism and genuine puzzlement. Some researchers argued that the observations must be wrong, that the debris mass had been overestimated by assuming incorrect optical properties for the dust, or that the expansion velocities were actually lower than measured and contaminated by line-of-sight projection effects. Others took the observations at face value and concluded that something genuinely unusual had occurred, either an improbable combination of circumstances or a new phenomenon not yet understood. A few suggested exotic explanations involving dark matter, primordial black holes, or other speculative physics that would be invoked only after all conventional possibilities had been exhausted. Patterns in the chaos. 4 days after the collision, when the debris cloud had expanded enough to resolve its structure clearly, the James Webb Space Telescope turned its infrared eye toward 3I Atlas. JWST operates at wavelengths from 0.6 to 28 micrometers, spanning near-infrared through mid-infrared, a regime where dust, grains and icy particles emit thermal radiation that reveals their temperature and composition. The telescope's resolution and sensitivity are unmatched, allowing detailed observations impossible from ground-based observatories hampered by Earth's atmosphere. The images revealed structure that made no immediate sense. The debris was not distributed randomly as expected for an explosion or impact event. Instead, it formed a complex pattern of filaments and arcs spiraling outward from the nucleus in an organized geometry that appeared almost deliberate. At first glance, the pattern resembled a pinwheel or spiral galaxy viewed face-on, with multiple arms wrapping around a central bright core. But this was not a galaxy. It was expanding debris from a disrupted comet, material that should be spreading chaotically in all directions. Image analysis confirmed the visual impression. The debris contained at least 7 distinct spiral arms extending radially outward from the nucleus. These arms were separated by angular intervals averaging 51.4 degrees, very close to the 43 degrees that would result from 7 evenly spaced sources located around the nucleus. Statistical analysis showed that the probability of 7 randomly placed structures falling into such regular spacing was less than 1%. Either the spacing was a coincidence, which seemed unlikely, or the disruption process had somehow organized the ejector into 7 preferred ejection directions. The spiral arms themselves showed remarkable consistency. Each arm could be traced from near the nucleus out to distances exceeding 50,000 kilometers, and throughout that range, each arm maintained a consistent pitch angle, the rate at which the spiral wrapped around the center. The measured pitch angle was approximately 12 degrees, meaning the spiral made one complete revolution every 30 degrees of radial distance. This uniformity was not what models of cometary fragmentation predicted. Natural fragmentation produces structures reflecting the nucleus's rotation and the distribution of active vents. But those structures typically show significant irregularities and variations because the nucleus is not a uniform sphere and the vents are not identically strong or evenly distributed. Fine structure within the spiral arms revealed additional organization. Each arm showed variations in brightness corresponding to clumps of denser material embedded within the more diffuse background. These clumps were not randomly spaced. Fourier analysis, a mathematical technique that identifies periodic patterns in data, revealed a strong signal at a spatial frequency corresponding to clumps separated by approximately 950 kilometers. This periodicity persisted along each of the 7 spiral arms, suggesting that whatever process created the clumps operated consistently across the entire debris field. The spacing between clumps allowed estimation of the timescale for their formation. If material in the debris cloud was moving at 800 meters per second, as spectroscopic measurements indicated, then 950 kilometers corresponds to about 20 minutes of travel time. This suggested that material was being ejected in discrete pulses separated by roughly 20 minutes rather than continuously. The total duration of enhanced brightness lasted about 4 hours from the initial surge through the second brightening phase. 4 hours divided into 20-minute intervals allows for 12 discrete ejection pulses. The 2-stage brightening observed photometrically might represent an averaging of these individual pulses, which would blur together in time-averaged measurements that lacked sufficient temporal resolution. Pulsed ejection of material from comets is known but not common. Some comets show quasi-periodic outbursts driven by the rotation of the nucleus, where active regions on the surface rotate into and out of sunlight, causing the outgassing rate to vary with a period equal to the rotation period. For 3I, Atlas, the rotation period was 8.3 hours. The 20-minute period observed in the debris structure bore no obvious relationship to the rotation period. It was neither an integer fraction nor a simple multiple. Something other than rotation was driving the pulsations. The spiral structure itself required explanation. Spirals are common in astrophysics. Spiral galaxies display prominent arms where stars and gas are concentrated. Planetary nebulae, the shells of gas ejected by dying stars, often show spiral patterns when the central star has a binary companion whose gravitational influence shapes the outflow. Hurricane-like storms in planetary atmospheres develop spiral structures from the combination of rotation and radial flows. But cometary debris clouds do not typically show spiral structure. The material simply expands radially outward in all directions, modified slightly by solar radiation pressure that pushes smaller particles more strongly than larger ones. Creating a spiral requires either rotation of the source or rotation of the medium through which the material is expanding. For 3I, Atlas, the nucleus was rotating with an 8.3-hour period. If material was ejected continuously from fixed vents on the rotating nucleus, it would indeed form a spiral pattern in space. This is the explanation for the spiral dust trails observed around some comets. But the pitch angle of such spirals depends on the rotation period and the expansion velocity. For 3I, Atlas's rotation period of 8.3 hours and measured expansion velocity around 800 meters per second, the predicted pitch angle would be roughly 2 degrees, much tighter than the observed 12 degrees. The observed spiral was too loose to be explained by rotation alone. Perhaps the ejection direction was precessing, rotating around the nucleus at a rate different from the nucleus's own rotation. Precession occurs when a spinning object wobbles, like a spinning top that traces out a circle as its axis tilts. If 3I, Atlas's rotation axis, was precessing, active vents on the surface would point in systematically varying directions as the nucleus rotated and precessed simultaneously, potentially creating complex patterns in the ejected material. But precession periods for objects the size of 3I, Atlas, are typically much longer than rotation periods, spanning days to months rather than hours. A precession period short enough to explain the observed spiral structure would require either extreme conditions that should have been detected in earlier observations, or a sudden change in the nucleus's spin state triggered by the collision itself. Comparisons to other astrophysical spirals provided limited guidance. Spiral galaxies form their arms through density wave theory, where gravitational interactions between stars create regions of enhanced density that rotate slowly through the stellar disk. The spiral pattern is not material, but rather a density enhancement, like a traffic jam that moves along a highway even though individual cars move at different speeds. This mechanism relies on gravitational interactions across vast distances and is irrelevant for a debris cloud only tens of thousands of kilometers across. Planetary nebulae spirals arise from binary star interactions. If the dying star has a companion, the companion's gravity distorts the outflowing gas, creating spiral patterns. The mechanism works because the outflow velocity is slow enough that the gas has time to respond to the companion's gravity over the timescale of one orbital period. For 3I, Atlas, any companion massive enough to shape the debris field through gravity would have been detected long before the collision. Small companions like moons are possible, but would need to be orbiting extremely close to the nucleus to exert sufficient tidal forces, and such close orbits are unstable for objects only 4 kilometers across. Magnetic fields offered another possible organizing mechanism. In stellar and planetary magnetospheres, charged particles follow magnetic field lines, creating organized structures in ionized gas. If the debris from 3I, Atlas, was ionized, and if magnetic fields were present, the expanding material might follow field lines rather than moving in straight radial paths. But comets are not magnetized. Measurements by spacecraft that have visited comets found no evidence for intrinsic magnetic fields. The interplanetary magnetic field carried by the solar wind has strengths around 5 to 10 nanotesla at 1.8 AU, far too weak to significantly deflect debris particles with any substantial mass. Magnetic effects are important for ions and electrons in the cometary plasma tail, but negligible for dust, grains, and larger fragments. One research group proposed that the spiral structure was an optical illusion created by viewing a 3-dimensional structure from a particular angle. If the debris cloud was actually a series of expanding shells or cones oriented in specific directions, projection effects could create apparent spirals that were not present in the actual 3-dimensional distribution of material. This geometric argument had merit. Confirming or refuting it required observing the debris cloud from multiple angles over time as Earth's motion changed the viewing geometry, or using other telescopes located at different positions in the solar system to provide stereoscopic views. The regularity of the patterns remained the central puzzle. Nature produces order through specific physical processes that favor certain outcomes over others. Crystals form regular lattices because atomic bonds prefer specific angles and distances. Snowflakes develop hexagonal symmetry because of the molecular structure of ice. Spiral galaxies form because gravitational instabilities favor certain patterns. But for 3I, Atlas, none of the known processes that produce ordered structures seemed applicable. The debris patterns were too regular to dismiss as coincidence, yet no convincing physical mechanism had been identified that would naturally produce 7 evenly spaced spiral arms with consistent pitch angles and periodic brightness variations. Some scientists began to wonder whether the patterns contained information, whether the organized structure was trying to tell observers something about the event that created it. This is the instinct of pattern-seeking minds facing puzzling observations, but without a theory that predicts such patterns and explains their significance, finding meaning in them is premature. The patterns are real. What they mean remains unknown. Collision physics. Understanding what happened to 3I, Atlas, requires understanding the physics of high-velocity collisions, one of the most intensively studied phenomena in planetary science. When objects collide at speeds of several kilometers per second or more, the impact is fundamentally different from everyday collisions at human speeds. Material strength becomes less important than momentum and energy. Solid rock behaves like fluid. Temperatures and pressures reach extremes found nowhere else in the solar system outside of planetary interiors and stellar atmospheres. NASA's Deep Impact mission in 2005 provided the best direct measurements of collision physics in a cometary target. The mission fired a 370 kilogram copper projectile into Comet Tempel 1 at 10.2 kilometers per second. The impact excavated a crater and produced a debris plume visible from Earth. Analysis of the brightness and spectroscopy of the plume revealed that the impactor had excavated approximately 10,000 tons of material per ton of projectile mass, far more than typical for solid rock targets. This high ejection efficiency reflected Tempel 1's porous structure, with density around 400 kilograms per cubic meter, much lower than solid ice or rock. The comet was more empty space than solid material, with a rubble pile structure that allowed energy to be channeled efficiently into breaking apart weakly bound aggregates. The deep impact observations matched laboratory experiments on porous targets. When researchers fire projectiles into targets with controlled porosity, they find that increasing porosity increases the mass of material ejected per unit of impact energy. The relationship is not linear. Doubling the porosity more than doubles the ejector mass because highly porous materials fragment more easily. The mechanism involves crushing of the porous structure around the impact point, which releases energy as stored elastic deformation is suddenly relieved. This released energy contributes to driving material outward, supplementing the impactor's kinetic energy. Scaling these results to 3I, Atlas, required assumptions about the nucleus's porosity and strength. If 3I, Atlas, had porosity similar to Tempel 1, around 70% empty space, and if the ejection efficiency was comparable, then producing 100 million kilograms of ejector would require an impactor mass around 10,000 kilograms. This corresponds to a spherical rock-like object approximately 3 meters in diameter, significantly smaller than the 10-meter estimate based purely on energy considerations. The discrepancy suggests that ejection efficiency was higher than typical, or that additional energy sources beyond the impactor's kinetic energy contributed to the event. Shockwave physics provides detailed understanding of what happens at the moment of impact. When the projectile first contacts the target, the sudden deceleration creates enormous pressure at the contact point. For an interstellar velocity of 25 kilometers per second, the initial shock pressure exceeds 100 gigapascals, 1 million times atmospheric pressure. At these pressures, solid materials compress substantially. Rock densifies by 20 to 30%. Ice undergoes phase transitions to high-pressure forms that are denser and have different crystal structures than normal ice. The shock wave propagates outward from the impact point at the speed of sound in the compressed material, typically 4 to 8 kilometers per second, depending on composition. As the wave expands, it weakens. Pressure decreases with distance from the impact point. At some distance, the pressure drops below the material's strength, and the shock wave becomes an elastic wave that can fracture material but no longer produces permanent deformation or vaporization. The radius at which this transition occurs depends on the impact energy and the material properties. Behind the expanding shock front, material is set in motion. Particles accelerate away from the impact point, acquiring velocities that depend on the local shock pressure. Near the impact site, where pressures are highest, material is vaporized or melted and moves at velocities approaching the original impact velocity. Farther out, where pressures are lower, solid fragments are ejected at lower velocities. The distribution of ejector velocities typically shows a power law relationship, with most material moving slowly and a small fraction moving at high speed. The shock wave also reflects off free surfaces and internal boundaries. When the shock reaches the backside of the target or encounters a large void within the material, part of the wave reflects back toward the impact point. This reflected wave is a tensile wave, pulling material apart rather than compressing it. Tensile waves cause spallation, the ejection of fragments from surfaces opposite the impact. In some impacts, spallation can eject more material than the direct excavation from the impact site. Temperature evolution during impacts is complex. The initial shock compression heats material to thousands of Kelvin near the impact point. The temperature depends on the shock pressure and the material's equation of state, the relationship between pressure, density, and temperature. For typical shock pressures in cometary impacts, peak temperatures range from 1000 to 5000 Kelvin, hot enough to vaporize ice, but not necessarily rock. The hot material expands rapidly as pressure releases, cooling adiabatically as it does work against the surrounding material. Cooling rates are extremely fast, millions of degrees per second initially, slowing as material expands and temperatures drop. Producing the persistent high temperatures observed in 3I, Atlas's debris required either very efficient shock heating, ongoing energy input after the initial impact, or conditions that prevented rapid cooling. One possibility involved secondary collisions within the debris cloud. If the initial impact fragmented the nucleus extensively, creating numerous large pieces moving at different velocities, these pieces could collide with each other as the debris expanded, generating additional shock heating. Each collision would produce hotspots that contributed to the overall thermal emission. For this mechanism to work, the debris cloud needed to contain a substantial population of kilometre-scale or larger fragments, not just fine dust and small pebbles. The Shoemaker-Levy 9 impacts on Jupiter in July 1994 demonstrated the phenomenal energies achievable in cosmic collisions. The largest fragments of the disrupted comet, estimated at 1 to 2 kilometers diameter, struck Jupiter's atmosphere at 60 kilometers per second. The impacts released energy equivalent to millions of megatons of TNT, creating fireballs that rose thousands of kilometers above Jupiter's cloud tops and left dark scars the size of Earth that persisted for months. The impacts were so energetic that ground-based telescopes detected the flash from the explosions, even though the impacts occurred on Jupiter's far side, not directly visible from Earth. The Shoemaker-Levy impacts provided constraints on collision physics at extremely high velocities, but were not perfect analogues for 3I Atlas, because the target was Jupiter's atmosphere rather than a solid body. Atmospheric entry and explosion involve different physics than solid body impacts. The projectile does not excavate a crater, but instead deposits its energy in the atmosphere through ablation and shock heating, creating a fireball that expands and rises convectively. Understanding impacts on solid bodies required different observations and experiments. Asteroid collisions, while rarely observed directly, leave evidence throughout the solar system in the form of impact craters on planetary surfaces and asteroid families in the main belt. Asteroid families are groups of objects with similar orbits, indicating they originated from the breakup of a larger parent body. The largest families contain thousands of members ranging from kilometers to tens of meters across. Their existence demonstrates that catastrophic collisions occur regularly on geological timescales, breaking apart objects tens to hundreds of kilometers across. Numerical simulations of catastrophic disruptions show that completely shattering a 100-kilometer asteroid requires an impactor about 3 to 5 kilometers across, striking at 5 kilometers per second. Smaller impactors or lower velocities produce partial disruption, breaking off large fragments without destroying the target entirely. The simulations reveal complex patterns of fracturing and fragment ejection that depend sensitively on the target's internal structure. Monolithic solid bodies respond differently than rubble piles. Pre-existing fractures and voids channel shock waves in unexpected ways, creating ejection patterns that are difficult to predict without detailed knowledge of the internal structure. For 3I, Atlas, the observations suggested partial disruption that excavated perhaps 10% of the nucleus mass, but left the bulk of the object intact. This is consistent with an impact that was energetic enough to cause local catastrophic damage, but not energetic enough to shatter the entire nucleus. The survival of the nucleus provided constraints on the maximum impact energy, which in turn constrained the impactor properties. Yet the details did not fit standard models. The two-phase brightening, the geometric organization of the debris, the persistent high temperatures, the absence of detectable changes in the nucleus's trajectory, all pointed to something more complex than a straightforward impact and excavation process. If standard collision physics applied, some key aspect of the target, the impactor, or the collision geometry must have been unusual in ways that current models do not account for. Eyes on the sky. Detecting asteroids and comets is fundamentally a problem of searching vast expanses of sky for small, faint, moving objects. The challenges are considerable. Space is enormous. Objects are tiny relative to the distances involved. Most asteroids and comets are dark, reflecting only a small fraction of the sunlight that hits them. And they move, which means that detection requires observing the same regions multiple times to identify objects that shift position against the background of stars. Modern asteroid surveys have evolved dramatically since systematic searches began in the 1990 seconds. The Catalina Sky Survey, operating telescopes in Arizona, represents one of the most productive programs. CSS uses a 1.5-meter telescope equipped with a large CCD camera to image sections of the sky, then image the same sections again 30 to 90 minutes later. Software automatically compares the images, identifying objects that moved between exposures. CSS discovers several hundred near-Earth asteroids annually and has found thousands of main belt asteroids. The system excels at finding objects larger than about 300 meters that reflect enough sunlight to appear brighter than magnitude 20 or 21, the practical detection limit given typical exposure times and atmospheric conditions. The Panoramic Survey Telescope and Rapid Response System in Hawaii operates differently. Pan-STARRS uses a 1.8-meter telescope with an enormous 1.4 gigapixel camera that can image areas of sky much larger than traditional telescopes can cover in a single exposure. This wide-field capability allows Pan-STARRS to survey the entire visible sky multiple times per month, reaching magnitudes as faint as 23 or 24 inches good conditions. The trade-off is that each field is observed less frequently than CSS's more focused approach. Pan-STARRS excels at finding objects that move slowly, which typically means objects that are more distant, while CSS is better at catching objects that are close to Earth and moving quickly across the sky. The asteroid Terrestrial-impact last alert system takes yet another approach. ATLAS operates two identical 0.5-meter telescopes, one in Hawaii and one in Chile, that scan enormous swaths of sky each night. ATLAS prioritizes survey speed over sensitivity, imaging the entire visible sky every 2 nights, but only reaching magnitude 19 or so. This strategy is optimized for finding objects that are close to Earth and moving rapidly, providing the last alert for potential impactors that might have been missed by deeper surveys. An object heading toward Earth collision would brighten rapidly as it approached, eventually becoming bright enough for ATLAS to detect, even if it had been too faint for earlier discovery. Together, these surveys and others like them provide substantial coverage of near-Earth space. Yet gaps remain, both technical and fundamental. Technical gaps arise from limitations in telescope time, detector sensitivity, atmospheric conditions, and data processing capabilities. Observing time is finite. Even robotic telescopes spend only a fraction of each night scanning for asteroids, with the remainder devoted to weather delays, maintenance, calibration, and observations for other scientific programs. Detector sensitivity limits how faint an object can be detected. Current surveys typically reach magnitude 22 to 24, which corresponds to specific object sizes at specific distances depending on albedo. Atmospheric conditions degrade observations. Clouds block observations entirely. Atmospheric turbulence blurs images, reducing the ability to detect faint objects near the detection threshold. Light pollution from cities brightens the sky background, making faint objects harder to distinguish from the background. Moonlight has similar effects, washing out faint stars and asteroids during much of each month. Survey programs must work around these conditions, concentrating observations during new moon periods and dark skies. Data processing presents another bottleneck. Each night's observations from a major survey generate hundreds of gigabytes of image data. Software must process these images, identify candidate moving objects, track them across multiple images to confirm they are real rather than cosmic ray hits or other artifacts, compute preliminary orbits, and compare them to databases of known objects to identify new discoveries. This pipeline must run quickly enough that candidates can be flagged for follow-up observations the next night before they move out of range. Human reviewers verify candidates before submission to the Minor Planet Center, adding another step that requires skilled personnel. Fundamental gaps arise from the physics of detection and the geometry of orbits. Objects approaching from directions near the Sun in the sky are impossible to observe because telescopes cannot point close to the Sun without risking damage to sensitive instruments. This creates a cone-shaped blind spot, extending roughly 30 to 50 degrees around the Sunday. Objects in this cone remain invisible until they emerge far enough from the Sun's direction. The Chelyabinsk meteor in 2013 approached from this blind spot, striking without warning despite its 20-meter size. Space-based infrared observatories can partially mitigate this problem by observing from locations where the Sun's glare is less problematic, but no current mission provides comprehensive coverage of this region. Object brightness depends strongly on albedo, the fraction of incident sunlight that is reflected. Rocky asteroids typically have albedos around 10 to 20%, meaning they reflect 10 to 20% of sunlight and absorb the rest. But some asteroids have albedos as low as 3%, making them extraordinarily dark. These dark objects reflect only a third as much light as typical asteroids, making them appear fainter and harder to detect. Without independent measurements of an object's size, usually obtained through thermal infrared observations or radar. Determining albedo is impossible from optical brightness alone. A faint optical detection could indicate either a small bright object or a larger dark object. Velocity matters for detection. Surveys are optimized to find objects moving at typical near-Earth speeds around 10 to 30 kilometers per second relative to Earth. Software pipelines reject detections that move too fast or too slowly, assuming they are artifacts or are not near-Earth objects. This filtering is necessary to reduce false positives, but means that objects with unusual velocities might be missed. Comets from the Oort cloud can arrive at 50 or 60 kilometers per second. Interstellar objects can exceed 100 kilometers per second. If software is not tuned to recognize such fast motion, the object might streak through the image in ways that automated detection algorithms do not recognize as real moving objects. The 3I, Atlas impactor, whatever it was, evaded all of these detection systems. This non-detection constrains its properties, but leaves many possibilities. If the object was a typical rocky asteroid, its size must have been below the detection threshold given its distance and presumed albedo. At 1.8 AU from the Sun, a rocky asteroid with 10% albedo would need to be larger than about 8 to 10 meters to be reliably detected by surveys reaching magnitude 22. An object smaller than this could easily go undetected. If the impactor was this small, however, it must have been moving extremely fast to deliver the observed energy, faster than is typical for interstellar objects, raising questions about its origin and how it acquired such velocity. Alternatively, the impactor could have been larger but darker, with albedo below 3%. Such an object might be 15 to 20 meters across, but appear as faint as an 8-meter typical asteroid. Low albedo objects do exist. Some carbonaceous asteroids have albedos around 3 to 5%, but interstellar objects might have even darker surfaces if they accumulated layers of radiation-processed organic material during their journey through space. Detecting a very dark object requires either higher telescope sensitivity or waiting until it comes close enough to appear brighter. The impactor might also have approached from an unfavorable direction. If it came from within the exclusion zone around the Sun where telescopes cannot observe, it would remain invisible until emerging from that zone. For an object on a collision course with 3I, Atlas, the timing matters. If the object only emerged from the exclusion zone hours before impact, there would be insufficient time to detect, confirm, and alert observers, even if the object was bright enough to be seen. Radar detection offers an alternative to optical surveys, but has severe range limitations. Planetary radar systems at Arecibo, before its collapse in 2020, and the Goldstone Deep Space Network can detect asteroids by bouncing radio waves off them and measuring the echo. Radar works regardless of an object's optical brightness because it provides its own illumination, but radar range is limited to objects relatively close to Earth, typically within a few tens of millions of kilometers. At 1.8 AU, 3I, Atlas, was about 270 million kilometers from Earth, far beyond radar detection range. Even if the impactor had been large and metallic, perfect for radar detection, it would have been invisible to radar at that distance. Space-based infrared surveys detect asteroids by their thermal emission rather than reflected sunlight. All objects warmer than absolute zero emit thermal radiation. At typical asteroid distances from the Sun, this emission peaks in the mid-infrared around 10 micrometers wavelength. An infrared telescope can detect this emission regardless of the object's albedo. The NEOWISE mission, which operated from 2013 to 2024, discovered thousands of asteroids using this technique including many dark objects that had been missed by optical surveys. The proposed Near-Earth Object Surveyor mission would continue this work with a dedicated space telescope optimized for finding asteroids in thermal infrared wavelengths. If launched and operated as planned, NEO Surveyor would dramatically improve detection of dark asteroids and objects approaching from directions near the Sunday. The implications of the 3I Atlas detection failure extend beyond asteroids to the broader question of impact hazards. Earth has been bombarded throughout its history. Craters pockmark the surface of every solid body in the solar system. Most impacts occur in oceans or remote areas where human population is sparse, causing no casualties. But occasionally, impacts occur in populated regions or are large enough to have global consequences. The Tunguska event in 1908, caused by an object probably 50 to 60 meters across, flattened 2,000 square kilometers of Siberian forest. Had it occurred over a city, casualties would have numbered in the tens or hundreds of thousands. The Chicxulub impact 66 million years ago, caused by an object 10 to 15 kilometers across, triggered environmental catastrophes that contributed to the extinction of the dinosaurs and many other species. Current planetary defense strategies focus on finding large objects with years or decades of warning time. If a threatening asteroid were discovered decades before projected impact, deflection missions could nudge it onto a safer trajectory with relatively modest interventions. NASA's Double Asteroid Redirection Test in 2022 demonstrated that crashing a spacecraft into an asteroid at high speed could change its orbit measurably. The impact shortened the orbital period of the asteroid Dimorphos by 33 minutes, confirming that kinetic impactors work as deflection mechanisms. With sufficient warning time, multiple spacecraft could deliver enough momentum change to steer an asteroid completely away from Earth. But all of this depends on detection with sufficient warning time. Interstellar objects present unique challenges because they arrive from outside the solar system on hyperbolic trajectories, visiting once and departing. If an interstellar object happened to be on a collision course with Earth, the warning time might be measured in months rather than years or decades. Current deflection strategies require years to implement. Time to design and build the spacecraft, time to launch and reach the target, time for the deflection to alter the trajectory enough to miss Earth. Responding to an interstellar threat with months of warning would require capabilities that do not currently exist, including spacecraft kept on standby and ready to launch on short notice. The probability of such an event is extremely low. The rate of interstellar objects passing through the inner solar system is estimated at a few per year, and the cross-sectional area of Earth is tiny compared to the solar system's expanse. The chance of an interstellar object hitting Earth in any given year is far lower than the chance of a solar system, asteroid, or comet impact. But the 3I Atlas event demonstrates that collisions do occur and that the universe can surprise us. Planning for low probability but high consequence scenarios is part of responsible planetary defense, even when the scenarios seem unlikely. Implications. The 3I Atlas collision, regardless of its ultimate explanation, reveals how much remains unknown about the environment of the solar system and the galaxy beyond. The inventory of objects in the solar system is incomplete. While the major planets, their moons, and the largest asteroids are well catalogued, smaller objects numbering in the millions remain undiscovered. Comets from the Oort cloud arrive unpredictably, their orbits perturbed by passing stars that send them sunward on timescales of millions of years. Interstellar objects pass through regularly, though we have confirmed only a handful because detection requires that they pass close enough to be noticed. Interstellar object collision rates are poorly constrained because the population size is uncertain. Before ʻOumuamua in 2017, the number of confirmed interstellar visitors was 0. Now we have 3 confirmed cases in 8 years. Statistical models based on these few detections estimate that interstellar objects 1 kilometer or larger might pass within Jupiter's orbit at a rate of several per year, with smaller objects vastly more numerous. But these estimates carry enormous uncertainties because detecting interstellar objects requires that they pass close to Earth or develop visible cometary activity. Small, dark, inactive objects would go entirely unnoticed, even if they pass through the inner solar system. If interstellar objects are as abundant as these estimates suggest, collisions between them and solar system bodies might be more common than chance would predict. Both populations are not distributed randomly. Solar system objects concentrate near the ecliptic plane where most orbits lie. Interstellar objects might also show preferred trajectories if their ejection from parent planetary systems and subsequent motion through the galaxy create directional biases. The Sun's motion through the galaxy means that interstellar objects are more likely to be encountered from the direction the Sun is moving toward, creating a collision hotspot if both interstellar and solar system objects are more abundant along certain trajectories. The consequences of such collisions extend beyond scientific curiosity to practical planetary defense. If collisions between interstellar and solar system objects occur regularly, even if rarely, they could contribute to the impact flux at Earth. Historical impact rates are estimated from the number and ages of craters on Earth and the Moon, combined with population models of near-Earth asteroids and comets. If interstellar objects contribute significantly to this flux, impact probability estimates would need revision. The practical effect would likely be small because interstellar objects are outnumbered by solar system natives by vast factors. But even a small contribution matters when assessing rare but catastrophic risks. Interstellar objects also pose unique challenges for defense. Solar system asteroids and comets orbit the Sun on predictable paths that can be calculated centuries in advance once discovered. This predictability allows long-term impact forecasts and planning of mitigation strategies. Interstellar visitors follow hyperbolic trajectories through the solar system just once. They cannot be predicted until detected, and they might have velocities higher than solar system objects, making deflection more difficult. Current deflection techniques rely on gradually changing an asteroid's velocity over time, leveraging the butterfly effect of orbital mechanics, where small changes applied early lead to large trajectory differences later. For an interstellar object detected months before potential impact, there might be insufficient time for gradual deflection to work. Alternative approaches involving nuclear explosives to rapidly alter trajectories might be necessary, technologies that are technically feasible but politically and legally complex to deploy. The 3I, Atlas, collision also highlights our incomplete understanding of the material properties of objects from other star systems. Our solar system formed from a specific disk of gas and dust, with a particular chemical composition reflecting the local galactic environment. Other star systems form in different parts of the galaxy with different compositions, and the resulting comets and asteroids might differ in systematic ways. Some regions of the galaxy are metal-rich, enriched by many generations of supernovae that produced heavy elements. Others are metal-poor, containing mostly hydrogen and helium with traces of heavier elements. The composition of planetesimals formed in these environments would reflect these differences, potentially creating comets with unusual ice mixtures or asteroids with atypical mineral compositions. Understanding this diversity matters for theories of planet formation and the chemical evolution of galaxies. Every interstellar visitor offers a sample from a different planetary system, a chance to study materials formed under different conditions light years away. The spectroscopy of 3I, Atlas, before the collision, revealed a composition similar to solar system comets, but subtle differences in isotope ratios or trace element abundances could reveal information about the chemical history of its birth environment. If more interstellar objects can be studied in detail, patterns might emerge showing how planetary system composition varies across the galaxy and how this affects the types of planets and moons that form. The geometric patterns in 3I, Atlas's debris, raise questions about fragmentation physics applicable beyond this single event. Understanding how objects break apart informs interpretations throughout planetary science. Asteroid families, groups of objects with similar orbits indicating common origin from the breakup of a larger parent, preserve information about ancient collision events. The size distribution of family members, their rotation rates, and their spectral properties all constrain the physics of the original disruption. Better fragmentation models improve our ability to reconstruct solar system history from these fossil records. Planetary defense strategies also depend on understanding how asteroids break apart. If an asteroid threatens Earth and cannot be deflected enough to miss completely, fragmenting it into smaller pieces that disperse might reduce the damage. Many small impacts spread over a region cause less destruction than one large impact concentrated at a point. But this strategy only works if the fragmentation can be controlled to ensure the pieces disperse rather than holding together and still striking Earth as a cluster. The Deep Impact mission demonstrated intentional fragmentation on a small scale, but scaling to kilometer-sized asteroids requires understanding how fracture propagates through varied internal structures. The event also demonstrates the value of sustained monitoring programs. If 3I, Atlas, had not been under regular observation by multiple telescopes, the collision might have been missed entirely or recorded only as a brief, unexplained brightness spike without context. The detailed data available because astronomers were already watching allowed analysis that would otherwise be impossible. This argues for maintaining and expanding survey programs even when no immediate threats are apparent. Scientific knowledge accumulates through sustained observation, and rare events like collisions require long monitoring campaigns to have any chance of being witnessed. The broader implication is that the universe retains the capacity to surprise. Modern astronomy has catalogued billions of galaxies, measured the expansion history of the universe, detected gravitational waves from merging black holes, and imaged the event horizon of supermassive black holes. These achievements might create an impression that the cosmos is well understood, that only details remain to be filled in. The 3I, Atlas event reminds us that even nearby, in our solar system's neighbourhood, phenomena occur that do not fit easily into existing frameworks. Each surprise, each anomaly, each unexplained observation is an invitation to deeper understanding, to questioning assumptions, to expanding theories to accommodate new reality. The collision might ultimately be explained through refined models of impact physics or better understanding of cometary structure. It might reveal new phenomena involving material properties or collision dynamics not previously encountered. It might remain partially unexplained, joining a list of puzzling observations that await future insights. Regardless of the outcome, the event has already contributed to scientific progress by forcing researchers to think carefully about detection capabilities, impact physics, and the properties of interstellar objects. The questions it raises will drive research for years, and the answers, when they come, will enhance our understanding of the cosmic environment Earth inhabits. The unsolved mystery. 6 months after the collision, 3I Atlas continues along its trajectory toward the outer solar system. The debris cloud has dispersed, spreading into a thin stream of particles that will take years to clear completely as radiation pressure from sunlight gradually pushes the smallest grains away and gravitational interactions with planets perturb the larger fragments. Follow-up observations continue, though less intensively now that the initial excitement has subsided. Astronomers track the comet's brightness, looking for signs of continued activity or delayed effects from the collision. So far, 3I Atlas has remained relatively quiescent, its brightness fading steadily as it moves farther from the Sun and solar heating declines. No definitive explanation for the October 12th event has emerged. The impact hypothesis remains the leading candidate favoured by most researchers, because impacts are known to occur and the energy budget is at least plausible, even if the details are problematic. But the specifics resist resolution. Was the impactor a rare iron-rich asteroid, dense and dark? Was it a conventional rocky object moving at unusually high velocity? Was it something else entirely, an object with properties not typically encountered? Each possibility explains some observations while struggling with others. Research groups around the world have published competing models in peer-reviewed journals. One paper argues that the impactor was indeed a small iron asteroid, perhaps 5 to 8 meters in diameter, with albedo below 3%, making it effectively invisible to optical surveys. Iron delivers energy efficiently due to its high density, and iron's high melting point means more energy goes into ejecting material rather than vaporizing the impactor itself. The paper presents detailed numerical simulations showing that an iron impactor at 25 kilometers per second can reproduce the total ejector mass and expansion velocities observed. Critics note that iron asteroids are rare even in the solar system, comprising less than 10% of the near-Earth population, and question whether an interstellar iron asteroid is plausible given the rarity of iron-rich planetary formation environments. A second paper proposes that the collision triggered runaway vaporization of super-volatile ices buried beneath 3I Atlas's surface. The paper argues that the nucleus contained deposits of highly volatile materials like carbon monoxide or molecular nitrogen ice, which remained solid at temperatures as low as 20 to 30 Kelvin. These deposits were hidden beneath an insulating crust of darker, less volatile material that prevented them from escaping earlier. The initial impact, even if small, fractured the crust and exposed the supervolatile deposits to sudden heating. The resulting explosive vaporization excavated far more material than the impact alone could produce. Numerical models show that sudden vaporization of a few million kilograms of carbon monoxide ice could release energy comparable to what was observed. Skeptics point out that maintaining supervolatile ice reservoirs requires specific thermal and structural conditions that are difficult to sustain in a nucleus only 4 kilometers across with modest internal gravitational compression. A third paper suggests magnetic field generation and interaction. The authors propose that the high-velocity impact created powerful transient magnetic fields through a process called impact-generated magnetization. When rocks are shocked to high pressures, thermoelectric and electrokinetic effects can generate strong magnetic fields lasting seconds to minutes. If 3I Atlas contained materials susceptible to magnetization, perhaps magnetite or iron-bearing silicates, portions of the ejector might have become magnetized. The interaction between magnetized debris and the interplanetary magnetic field could organize the expanding material through magnetic tension forces, creating the observed geometric patterns. Computer simulations demonstrate that such organization is possible under idealized conditions. Critics question whether the required magnetic field strengths can be sustained long enough and whether cometary material contains sufficient magnetizable components to produce observable effects. The geometric patterns continue to perplex researchers even after months of analysis. One team conducted extensive statistical tests on the spiral arm, spacing, and pitch angles, comparing them to thousands of simulated random fragmentation events. The result showed that the observed regularity is unlikely to occur by chance, with a probability less than 1% under most fragmentation models. This strengthens the case that some organizing principle structured the debris, but does not identify what that principle might be. Another team explored projection effects, calculating how three-dimensional structures would appear when viewed from various angles. They found that certain combinations of expanding cones or jets, if viewed from specific directions, could create apparent spirals even when no true spiral exists in 3 dimensions. This interpretation requires that Earth happen to be positioned at just the right angle to see the effect, which is possible but not strongly supported by additional evidence. High-resolution spectroscopic monitoring by the European Southern Observatory's Very Large Telescope has tracked the evolution of emission lines in the debris over the months since the event. The forbidden oxygen and nitrogen lines that indicated 10,000 Kelvin temperatures persisted for several days before fading, longer than simple cooling models predict, but not impossibly long if the hot gas was reheated by secondary collisions within the debris cloud. The molecular emission features that were initially difficult to identify have been confirmed as belonging to various carbon-bearing molecules produced when complex organics are thermally processed. This chemistry is consistent with impact heating, but provides limited constraints on the impactor properties. The detection failure remains perhaps the most troubling aspect of the event. Multiple research teams have conducted exhaustive searches of archival survey images, looking for any trace of the impactor in observations taken hours or days before the collision. State-of-the-art image processing techniques, including stacking multiple images to increase sensitivity and machine learning algorithms trained to identify faint moving objects, have been applied. Nothing has been found. The limits these searches place on impactor brightness, combined with distance estimates, imply either that the object was remarkably dark, with albedo below 2%, or that it was approaching from a direction that happened to be in a gap in survey coverage. To address this uncertainty, some astronomers have proposed enhanced monitoring programs targeting interstellar objects. When the next interstellar visitor is discovered, multiple telescopes would observe it continuously, watching not just for brightness changes, but for any indication of other objects in the vicinity. This monitoring would be expensive in terms of telescope time, but might catch similar events before they occur, rather than only observing the aftermath. The challenge is that interstellar objects are discovered at a rate of less than 1 per year currently, and not all pass close enough to the Sun to be monitored intensively. Implementing a comprehensive monitoring program might require waiting years between suitable targets. Efforts to improve detection capabilities are progressing. The Vera C. Rubin Observatory in Chile completed construction and entered commissioning phases, with full science operations expected to begin soon. Rubin's 8.4-meter mirror and 3.2 gigapixel camera will allow it to survey the entire visible sky multiple times per week, detecting objects fainter than magnitude 24. This sensitivity improvement means that asteroids in the 5 to 10 meter size range could be detected at greater distances than current surveys reach. If another collision occurs while Rubin is operational, the impactor might be seen before impact, answering one of the key questions raised by 3I, Atlas. The Nancy Grace Roman Space Telescope, scheduled for launch this decade, will include infrared survey capabilities useful for finding dark asteroids. Operating from space eliminates atmospheric absorption and background that limit ground-based infrared observations. Roman's survey might discover populations of very dark objects that optical surveys miss, providing statistics on how common such objects are and whether they pose a greater threat than currently estimated. The proposed Near-Earth Object Surveyor mission would be even more capable for asteroid detection. NEO-Surveyor is designed specifically to find and characterize near-Earth objects using infrared observations that detect thermal emission. Operating from space at a location away from Earth's thermal glow, NEO-Surveyor would detect asteroids based on their temperature rather than reflected sunlight. This makes detection independent of albedo and allows observation of objects approaching from directions near the Sun where optical telescopes cannot look. If funded and launched, NEO-Surveyor could transform planetary defense capabilities by closing many of the detection gaps that currently exist. The 3I Atlas collision serves as a case study in how science responds to unexpected observations. When data do not fit existing models, researchers propose alternative explanations, devise new models, and conduct additional observations to test competing hypotheses. This process takes time. Unusual observations require careful verification to ensure they are real and not artifacts of measurement errors or data processing bugs. Once observations are confirmed, developing theories that explain them requires creativity, mathematical rigor, and consistency with established physics. Testing theories requires new observations or experiments that can distinguish between competing ideas. For 3I Atlas, this process is ongoing and may take years to reach consensus. Some mysteries in astronomy remain unsolved for decades. Gamma-ray bursts were first detected in the 1960 seconds by satellites monitoring for nuclear weapons tests, but their origin was not understood until the 1990 seconds, when better observations revealed they came from exploding stars in distant galaxies. Fast radio bursts, discovered in 2007, are only now yielding to theoretical interpretation as more events are detected and their properties characterized. The nature of dark matter and dark energy remain unknown despite decades of research, though observations continue to constrain the possibilities. The 3I Atlas collision might follow a similar trajectory. It might be explained relatively quickly if a key observation provides the missing piece of the puzzle. A fragment from the debris might be recovered by a sample return mission, though the expense and technical challenges of reaching an object 1.8 AU from the Sun make this unlikely. Observations of similar events on other comets might reveal patterns that point toward the correct explanation. Advances in numerical simulations might allow more realistic modelling of impact processes that reproduce all the observed features. Or the mystery might persist, becoming one of those observations that future generations of astronomers revisit as new techniques and theories become available. Solar system exploration is still young. Humans have been seriously studying asteroids and comets for less than a century. Space telescopes have existed for decades. The inventory of interstellar objects is barely begun. As capabilities improve and knowledge deepens, questions that seem intractable today might yield to future insights. What is certain is that 3I Atlas will continue to fascinate researchers and space enthusiasts. The event combined drama, mystery, and scientific significance in ways that capture imagination while provoking serious investigation. The geometric patterns in the debris, the energetic disruption defying easy explanation, the detection failure that highlights blind spots in current surveys. All these aspects make 3I Atlas more than just another astronomical observation. It is a reminder that the universe remains full of surprises, that nature's complexity exceeds our current understanding, and that the cosmos rewards careful observation with discoveries that challenge and expand knowledge. By the time 3I Atlas crosses the heliopause in several thousand years, exiting the solar system and returning to interstellar space, it will be too faint to observe with any existing or planned telescope. The object will carry its secrets with it into the darkness, leaving behind the observations and data recorded during its brief passage through the inner solar system. Those observations will be studied by future generations, interpreted through frameworks and theories we cannot yet imagine, contributing to a cumulative understanding that builds across centuries. That is how science works. Each generation adds its observations and insights to the collective knowledge, and future generations build upon that foundation, reaching toward deeper truths about the cosmos and our place within it. The questions raised by 3I Atlas will be answered eventually, perhaps by insights derived from studying entirely different phenomena. Understanding of collision physics might advance through laboratory experiments on new materials. Detection capabilities might improve to the point where similar events are witnessed with full knowledge of the impactor's properties. Theoretical physics might reveal mechanisms that organize debris in unexpected ways. The path from mystery to understanding is never straight, but science has proven remarkably effective at eventually finding answers when observations persist and curiosity endures. Until then, 3I Atlas remains what it has been since October 12th, an unsolved mystery that invites explanation, a puzzle that challenges understanding, and a testament to the richness of phenomena waiting to be discovered in the vast universe around us. What NASA knows. NASA's Planetary Defense Coordination Office operates under a clear mandate to identify, track, and characterize asteroids and comets that could potentially threaten Earth. The office maintains comprehensive databases of near-Earth objects, calculates orbital trajectories decades into the future, and coordinates international efforts to ensure no dangerous object approaches Earth without warning. When 3I Atlas was discovered as an interstellar visitor, PDCO added it to tracking databases not because it posed any threat, but because understanding the population of interstellar objects contributes to assessing long-term risks and understanding galactic environments. After the October 12th collision event, PDCO issued a carefully worded statement acknowledging the disruption and emphasizing that 3I Atlas posed no danger to Earth. The statement noted that NASA was coordinating observations with international partners, that multiple telescopes were monitoring the object, and that scientific analysis was ongoing, with results to be published in peer-reviewed journals once studies were complete. The tone was measured, professional, and deliberately non-alarming, consistent with NASA's communication strategy for astronomical events that do not pose immediate public safety concerns. But the brevity and vagueness of the statement raised questions in the scientific community and among space enthusiasts. For an event as unusual and spectacular as the 3I Atlas collision, many expected more detail. What exactly had NASA's own telescopes observed? What did their models suggest about the impactor's properties? Were there implications for planetary defense strategies if objects could approach and collide with minimal warning? The public statement provided none of these details, leading to speculation about what NASA might know that it was not sharing. Behind the closed doors of NASA facilities and in email exchanges among researchers with government affiliations, a different conversation was occurring. Internal documents obtained later through Freedom of Information Act requests revealed active debate about the detection failure and its implications. If a 10-meter object, or whatever size was required to produce the observed disruption, could approach 3I Atlas without being detected by any telescope in the survey network, what did that say about detection capabilities for Earth-approaching objects? The planetary defense community takes this question seriously because their entire mission depends on detection. Finding potentially hazardous asteroids before they impact Earth, ideally with years or decades of warning time, allows for mitigation strategies ranging from trajectory deflection to civil defense preparations. The 2013 Chelyabinsk meteor provided a stark reminder of detection gaps. That 20-meter object exploded over Russia with energy equivalent to 500 kilotons of TNT, injuring over 1,500 people through window glass blown inward by the shockwave. No survey detected it before impact because its approach came from the direction of the Sun where telescopes cannot observe. The 3I Atlas event, while not threatening Earth, demonstrated that even away from the Sun's glare, objects of comparable size could evade detection under certain circumstances. One internal memo discussed revising estimates for the completeness of the near-Earth asteroid catalogue. Previous assessments, based on the detection rates of survey telescopes and statistical models of the asteroid population, concluded that NASA had found approximately 90 to 95% of near-Earth asteroids larger than 1 kilometer, and about 30 to 40% of objects larger than 140 meters. The congressional mandate tasked NASA with finding at least 90% of objects larger than 140 meters by specific deadlines. The failure to detect what presumably impacted 3I Atlas, if it was an object in the 10-meter size range, raised questions about whether the statistical models were too optimistic and whether smaller but still damaging objects were more numerous and harder to find than previously estimated. The memo proposed several responses. Enhancing survey cadence by observing fields more frequently could improve detection of fast-moving objects that might be in and out of a telescope's field of view between observation sessions. Extending survey coverage to higher ecliptic latitudes, above and below the plane where most solar system objects orbit, could find objects approaching from unusual directions. Developing infrared surveys that detect thermal emission rather than reflected sunlight could find dark objects that optical surveys miss. Each enhancement required resources, more telescopes, larger detectors, more computing power to process the flood of data, more personnel to analyze candidates and confirm discoveries. NASA's public reluctance to provide detailed technical explanations immediately after the event likely reflected multiple concerns. First, scientific caution demands not rushing to conclusions before analyses are complete. The peer review process exists to catch errors, verify calculations, and ensure that published results are sound. Jumping to announce interpretations that later prove incorrect damages institutional credibility and public trust in science. NASA learned this lesson from past incidents where premature announcements had to be walked back after more thorough analysis. Second, discussing what was not detected could be misinterpreted as admitting dangerous gaps in Earth's defenses. While it is technically accurate that small objects might evade detection under specific circumstances, publicizing those gaps risks causing undue public alarm. The actual probability of any particular small asteroid hitting a populated area on Earth is extremely low. Asteroid impacts that cause localized damage occur every few decades to centuries. Impacts large enough to threaten civilization are separated by tens of thousands to millions of years. The risk is real but manageable. An effective planetary defense requires steady, sustained investment in detection and tracking, rather than crisis-driven responses to individual events. Third, some of the discussion within NASA and partner organizations touched on sensitive topics related to national security and information sharing protocols. If an object on a collision course with Earth were detected with sufficient warning time, decisions about how and when to inform the public, what mitigation options to pursue, and how to coordinate international responses would involve complex policy questions extending far beyond NASA's authority. While no such object is currently known, the protocols for handling such scenarios are subjects of ongoing discussion among government agencies. International bodies, like the United Nations Committee on the Peaceful Uses of Outer Space, and space agencies worldwide. Discussing these protocols publicly without proper context and framing could lead to misunderstandings about current capabilities and plans. Interviews with NASA scientists involved in tracking 3I, Atlas, yielded carefully calibrated statements that acknowledged the unusual nature of the event while emphasizing ongoing analysis. One researcher explained that they were evaluating multiple scenarios to explain what they observed, that the data were complex and some aspects did not fit neatly into standard models, and that it was important to continue observations, gather more data, and let the peer review process work before drawing firm conclusions. Another scientist noted that events like this remind us how much we still do not understand about the diversity of objects in the solar system and interstellar space, and that every unusual observation is an opportunity to learn. These statements were both scientifically accurate and deliberately non-committal, a stance that satisfied neither those seeking definitive answers nor those suspecting that information was being withheld. But this is often how science proceeds at the frontiers of knowledge. When observations do not match expectations, researchers must carefully work through alternative explanations, checking calculations, verifying measurements, and considering possibilities that might initially seem unlikely. This process takes time, sometimes months or years. Public communication during this interim period requires balancing honesty about uncertainty with avoiding speculation that could be misleading. International space agencies provided their own analyses that largely paralleled NASA's cautious approach. The European Space Agency's Near-Earth Object Coordination Centre added the 3I Atlas event to their database and noted it in their regular impact monitoring reports. The language was technical and understated, befitting an organisation focused on objective tracking and risk assessment. The Russian Space Agency mentioned the event in their asteroid monitoring bulletins but offered no detailed analysis, likely because their observing facilities had limited coverage of 3I, Atlas's position in the sky during the critical timeframe. The Japanese Aerospace Exploration Agency issued a technical memorandum discussing the spectroscopic observations obtained by Japanese telescopes, focusing on the detection of unusual molecular features in the spectrum, but drawing no firm conclusions about their significance. The international coordination reflected how astronomical observations work in the modern era. No single nation has a monopoly on telescopes, data, or analytical expertise. Observations flow freely across borders through established data sharing agreements. When unusual events occur, researchers worldwide analyze the available data independently, and results are disseminated through scientific journals accessible to all. This openness benefits science by ensuring that errors are caught, alternative interpretations are considered, and the best explanations emerge through peer review and replication. It also means that attempts to suppress information would be nearly impossible. If NASA discovered something genuinely alarming about 3I, Atlas, maintaining secrecy would be difficult given the number of independent observers tracking the object and analysing publicly available data. What NASA knows about 3I, Atlas, is probably not dramatically different from what the broader scientific community knows. They have access to data from NASA-operated telescopes, including space-based assets like JWST and Hubble that provided some of the highest quality observations, but ground-based observatories around the world also obtained excellent data that is available to researchers globally. The advantage NASA has is institutional resources, teams of scientists, supercomputing facilities for running simulations, and organizational expertise in coordinating large observational campaigns. These resources allow for more thorough analysis, but do not provide exclusive knowledge unavailable to others. The 3I Atlas event will undoubtedly lead to refinements in planetary defense strategies, regardless of the eventual consensus explanation for what caused it. Even if the collision was a once-in-a-generation event involving improbable circumstances, it demonstrated that reality sometimes defies expectations, and that systems designed to protect Earth must account for rare possibilities. The search for understanding continues in observatories around the world. New telescopes come online with enhanced capabilities. Improved detectors reveal fainter objects. Advanced computer simulations model collision physics with increasing realism. Each advancement brings the possibility of breakthrough insights that finally explain what happened on October 12th when something massive struck an interstellar visitor and created patterns in the debris that looked almost intentional. The answer lies somewhere in the intersection of observation, theory, and perhaps phenomena not yet fully understood. Finding it requires patience, rigor, and the willingness to follow evidence wherever it leads, even into territories where current knowledge provides no map. This is the essence of scientific exploration, pushing boundaries, questioning assumptions, seeking truth through systematic investigation of the natural world. The 3I Atlas collision exemplifies why this work matters and why mysteries, far from being frustrations, are invitations to discovery that drive progress and expand human understanding of the cosmos. Oh, watch the skies with careful attention and open minds. After the event that generated it, available for future generations to examine with fresh perspectives and improved tools. What hit 3I Atlas remains unknown. Whether it was a dark asteroid, a fast-moving fragment, something exotic, or something entirely unexpected, the answer will eventually emerge through continued observation and analysis. The geometric patterns in the debris will be explained, whether through projection effects, magnetic fields, or mechanisms not yet considered. The detection failure will inform improvements in survey capabilities that close gaps and enhance planetary defense. The energy budget will be reconciled through better understanding of impact physics or recognition of additional energy sources. Science has proven remarkably effective at solving puzzles when data is available and researchers are motivated. The 3I Atlas mystery provides both. More definitive, placing stringent limits on how strongly dark matter interacts with normal matter. Could a dark matter particle or clump of dark matter have struck 3I Atlas? The idea seems far-fetched. Dark matter particles, if they are WIMPs, as many models suggest, would pass through the entire comet without interacting at all, except through extremely rare collisions with atomic nuclei. A single dark matter particle striking a single nucleus would deposit negligible energy, nothing remotely approaching the 100 trillion joules observed. Creating a significant effect would require either a dark matter particle with much stronger interactions than most models allow, contradicting the null results from detection experiments, or a scenario where many dark matter particles struck simultaneously, which seems contrived and unlikely without specific mechanisms to create such clustering. A different dark matter possibility involves hypothetical objects called dark matter nuggets or quark nuggets, proposed in some theoretical scenarios where dark matter exists in the form of macroscopic lumps rather than individual particles. These nuggets could range from grams to kilograms in mass, compressed to nuclear densities, making them incredibly small for their mass. A kilogram nugget might be smaller than a bacterium. If such an object passed through 3I Atlas, it would gravitationally attract and compress material along its trajectory, potentially releasing energy. But this mechanism faces challenges explaining the observed effects, and dark matter nuggets remain highly speculative, with no observational evidence supporting their existence. Primordial black holes offer another exotic possibility that has received serious attention in theoretical physics. In the first moments after the Big Bang, density fluctuations in the hot, dense primordial plasma could have collapsed directly into black holes without forming stars first. These primordial black holes could exist across an enormous range of masses, from subatomic to thousands of solar masses, depending on when and how they formed. Constraints from various observations rule out primordial black holes as the dominant form of dark matter, except in certain narrow mass ranges, but they could still exist as a small component of the dark matter population. A primordial black hole with mass around 10 tons would have an event horizon radius of approximately 10 to the negative 23 meters, far smaller than a proton. Such an object would be effectively invisible until it encountered matter. If it passed through 3I Atlas, it would gravitationally accrete material along its trajectory, heating the infalling matter through compression to high temperatures. The energy released could potentially explain the observed thermal emission and disruption. The accreted material would spiral into the black hole over timescales determined by the accretion rate, potentially maintaining high temperatures for hours as observed. The challenge with the primordial black hole hypothesis is explaining why one would happen to pass through 3I Atlas at that specific time and place. If primordial black holes are rare enough to have evaded detection in searches so far, the probability of one randomly intersecting a 4-kilometer comet during the brief time it was under intensive observation is vanishingly small. The galaxy is vast and mostly empty. Even if thousands of primordial black holes populate the solar system, which seems unlikely given observational constraints, the probability of one hitting any particular target remains extremely low. Some researchers have suggested that 3I Atlas itself might have unusual internal properties that made it susceptible to explosive disruption. Interstellar objects come from other planetary systems where formation conditions might differ from the solar system's. Could 3I Atlas have contained materials or structures not common in solar system comets? Could its composition have included exotic ices or chemical mixtures that react energetically when heated or compressed? Laboratory studies of cometary analog materials have explored how various ices behave under heating and compression. Water ice is the dominant component in most comets, but carbon monoxide, carbon dioxide, methane, and ammonia are also present. Some models propose that comets might contain clathrate, hydrates, cage structures where water molecules surround and trap smaller molecules like methane or carbon dioxide. Clathrates are stable at low temperatures but can destabilize if heated, releasing the trapped gases suddenly. If 3I Atlas contained large deposits of unstable clathrates, solar heating or a small impact might trigger catastrophic destabilization, releasing enormous amounts of gas in a short time. But explosive destabilization of clathrates faces quantitative problems. The binding energy of clathrates is relatively modest. and releasing trapped gases does not generate enough energy to explain the observed violence of the 3I Atlas event. The energy would come from the gas expansion work, which is limited by the pressure and volume involved. Calculations suggest that even complete destabilization of the entire nucleus would release energies 1 or 2 orders of magnitude less than observed. More exotic chemical scenarios involve reactive species that might be created under special conditions. Peroxides and superoxides, compounds containing oxygen-oxygen bonds, can react energetically when heated or subjected to shock. If interstellar chemistry or radiation processing created deposits of such compounds in 3I Atlas, they might detonate or combust when suddenly exposed by an impact or internal fracturing. But cometary chemistry is reasonably well understood from spectroscopic observations and spacecraft missions, and no evidence exists for large quantities of highly reactive peroxides or similar compounds in typical comets. Creating such materials would require unusual conditions during formation or subsequent processing that seem unlikely. The most speculative possibility, and the one that generates the most controversy, is that 3I Atlas, or the object that struck it, might not be natural. The idea that interstellar objects could be probes or artifacts from extraterrestrial civilizations gained attention after ʻOumuamua's unusual acceleration led some, most notably Harvard astronomer Avi Loeb, to suggest it might be an artificial light sail rather than a natural comet. The mainstream astronomical community overwhelmingly concluded that natural explanations for ʻOumuamua were sufficient, but the debate highlighted the challenge of distinguishing between unusual natural objects and hypothetical artificial ones. For 3I Atlas, the geometric patterns in the debris and the organized structure raise similar questions. Could the patterns be intentional? Could the collision have been deliberate rather than random? These questions are worth asking in the sense that science should not automatically dismiss possibilities without consideration. But the burden of proof for extraordinary claims is high, and extraordinary claims require extraordinary evidence. What would constitute evidence for artificiality? Proponents of the search for extraterrestrial intelligence suggest several criteria. First, the detection of narrow-band electromagnetic signals that cannot be produced by natural astrophysical processes would be strong evidence for artificial transmitters. No such signals have been detected from 3I Atlas or its debris. Second, observing structures or behaviors that defy natural explanation even after exhaustive consideration of conventional physics would be suggestive. The patterns in 3I Atlas's debris are unusual but not impossible to explain through natural means, and research into those natural explanations is ongoing. Third, detection of materials or isotope ratios that could not be created through natural nucleosynthesis and that point to artificial processing would be compelling. Spectroscopic analysis of 3I Atlas has found nothing that requires artificial origin. Without such evidence, the artificial hypothesis remains speculation unsupported by data. Natural processes can produce remarkable order and complexity. Crystals self-assemble into regular lattices. Spiral galaxies form through gravitational instabilities. Snowflakes develop intricate hexagonal symmetry. In each case, the underlying physics favors specific outcomes, creating patterns that might appear designed but emerge naturally from the interplay of forces and matter. Finding convincing natural explanations for 3I Atlas's patterns may require insights from unexpected areas of physics or discovery of new phenomena, but that is how science progresses. The value of considering exotic possibilities, even unlikely ones, lies in ensuring that conventional thinking does not blind researchers to genuinely novel phenomena. History provides examples of discoveries initially dismissed as impossible that later proved real. Meteorites were considered folklore until physical evidence became overwhelming. Continental drift was rejected by most geologists until plate tectonics provided the mechanism. The acceleration of the universe's expansion was so unexpected that cosmologists initially thought it was an error. Maintaining openness to new ideas while requiring strong evidence before accepting them is the balance that makes science both creative and reliable. For 3I, Atlas, the exotic explanations remain on the table but are not favoured by most researchers. The consensus is that more mundane explanations involving impact physics, unusual material properties, or geometric projection effects are more likely. But the investigation continues, and definitive answers may take years to emerge as observations accumulate and models are refined.